So once we have double integrals that are capable of telling us the mass of a region in 2 dimensions, then it's also an interesting question to ask where is the center of mass of that 2-dimensional region. This would be the same thing as asking sort of where would this figure, where would this region in 2 dimensions balance if we could balance it on the point of a pencil or something, right? So if I had a triangle that looked like this one, and if it had a uniform thickness and I was holding it in my hand, right, a piece of cardboard or something cut out in this shape, then where in this triangle could I put a balance point? What XY coordinates could I balance this triangle on? And the coordinates of that point are called the center of mass of the lamina. So how would we use multivariable calculus to do that? Well, we first need to know what is the total mass. That's just given by the double integral of the density function, just like the example we just did. But then the center of mass is found by finding what's called the first moment of the x variable and the first moment of the y coordinate. And what the first moment of a function is, I'm kind of using probability theory language here. The first moment is nothing more than the integral of that function over the region divided by the total mass of that region. So to find the x coordinate of the center of mass of a lamina, we're going to multiply the density function by x and then integrate that over my region and divide that whole value by the total mass of the region. For the y coordinate of the center of mass, we multiply the density function by y, integrate that, and divide that by the total mass. And so we end up needing to do a total of 3 integrals to find the center of mass of a lamina. We need the total mass, which is the denominator in both of these. And then we also need to do that integral again, but multiply that density function by an x, and again multiplying that density function by a y. That gives us the numerators of these centers of mass. So let's just talk through this example. So for this particular triangle, why don't we just do a quick heuristic first? Like, what if we could balance this triangle on the point of a pencil? What do we think would be approximate coordinates? So let's take a guess at where the center of mass is first, and then we'll do the calculation to see if we can figure out how to pinpoint it exactly. But what are your guesses on what the center of mass of this ought to be? The x coordinate of the center of mass is going to be an x value where there is exactly as much mass to the left of my point as there is to the right of my point. The y coordinate is going to have exactly as much mass above that point as below that point in my region. So probably y equals 1 is not going to be a good location for the center of mass, because anywhere that I try to balance this figure, if I tried to balance it on the edge of a ruler or something right here at y equals 1, there's definitely more mass if the density is uniform. There's more mass underneath than there is above. Now in this activity, they give us a density function that tells us that it's not uniform, but I kind of am just rather interested in doing this one as a uniform density problem, just so that we don't have to have that second piece of information, the density in our mind. So any other guesses on approximately where the coordinates of the center of mass for this thing might be? So here's a guess at approximately where this thing might balance. I don't know. When I look at this, it looks like maybe, I believe that it would probably balance from left to right at that point, but it still looks like it might be heavier below than above this point. So I might want to move the y coordinate down some. I don't know, maybe down to there? 2/3, 1/2. I know, so those are some guesses. But of course, the great thing about calculus is that we can and should actually do the work to figure out where is the balance point of this. So let's set that up and evaluate the integrals that would give us the x and y coordinates of this center of mass. So first of all, we have a type 1 description of this region that is in my Desmos worksheet that we were looking at a second ago. So let's get that description written in here. Description of the region as a type 1 region is going to tell us, get my equation editor out, that y is ranging between 0 and 2x, and x is ranging between 0 and 1. So there's my type 1 description of the region. And so to find the mass of this region, assuming uniform density, density equal to 1, so that what we're finding is really not the center of mass per se, because we don't have a density. Sometimes it's just called the centroid point. It's called the centroid rather than the center of mass. Okay, so if I assume a density equal to 1, then the total mass, in other words, the area, is just going to be the double integral over my region of 1 dA. And that's just the same thing as the area of this triangle. So rather than do out the calculus for this piece, let's just use geometry. Because we have a uniform density, we can get away with it here. So it's a triangle whose height is 2 and whose width is 1, and so its area is half of 2 times 1, which is equal to 1. So the total mass, or the area of this figure, is 1. And so now to find the first moment of the x-coordinate, that's the double integral over my region of x with respect to a. So this is just like the integral that you did in the previous problem where x was serving as a density. Here x is serving as a multiplier for my density when my density is 1. And so this is going to give me the x, the first moment of the x-coordinate. So using my description as a type 1 region, this is the integral from 0 to 1 of the integral from 0 to 2x of x with respect to y and then with respect to x. So when I do out that first of my 2 iterated integral steps, my antiderivative for x with respect to y is going to be x times y. And so I'll evaluate x times y from y equals 0 to y equals 2x. And so I'm going to get 2x times x, or 2x squared, minus 2x times 0. And so after one step, we just have the integral of 2x squared from 0 to 1. That antiderivative is 2x cubed over 3, evaluated from 0 to 1. That's going to be 2/3. And so actually, the x-coordinate of the center of mass is going to be 2/3 divided by the total mass. That's 2/3 divided by 1. Hey, it is actually exactly 2/3. So, great guess. So, x-coordinate of center of mass, centroid, is just going to be 2/3 divided by 1. Great. So that's the x-coordinate of the centroid. The y-coordinate seemed to be the one that was a little bit harder to eyeball, so let's find it. The first moment of the y-coordinate is just the double integral of the function y. Over the region D. So y with respect to area. So it's the integral from 0 to 1 of the integral from 0 to 2x of y with respect to y and then with respect to x. And so on my first integration step, the antiderivative of y with respect to y is half y squared. So now I'm integrating half y squared from, I'm evaluating half y squared from 0 to 2x. And so I'm getting half of 2x squared, which is going to give me 2x squared. Oh, interesting. That ends up with the same integrand that we had from before. And then I'm integrating that with respect to y. Wait a minute. No, this is with respect to x, sorry. And it's the same integral that we did before. It ends up being 2/3. So interestingly, the x-coordinate and the y-coordinate of this centroid are both 2/3. And that's something that I don't think we could have expected to happen before we actually did this work. We can't expect that the x and y coordinates are the same, but it just happened to be the case this time. So if we come back into the sketch, just to verify that our intuition is giving us something intuitive, when I place this point at 2/3, it tells me that right there is my balance point. That's the point at which this triangle would balance if it had a uniform density. So there is a centroid, or a center of mass, if we have a density function example for an application of multiple integrals. As you might expect, this also will work for regions in 3 space, so a solid region for a triple integral. We could find sort of the center of volume, or the centroid, using the same idea just by finding the first moments of the x, y, and z coordinate functions, dividing them by the total volume. When we get to triple integrals, we might see an example or two that looks something like that when we get there.